Hi all, this is Rieko Adriaens from Q-Mineral Belgium reporting on the results of the Reynolds Cup 2022. More specifically on the results of the round robin contest and the announcement of the top finishers at the end of the presentation. So what is the Reynolds Cup exactly? Well, it's a round robin test for quantitative mineral analysis in which different laboratories from all over the world can participate to test the performance and accuracy of their quantitative methods. This is important because, as you might know, quantitative mineralogical data are very difficult or even impossible to verify. Yeah? It's very hard to get the ground truth. So that's why round-robin contests exist, where samples are being prepared with a known composition and are being distributed among different labs who can then test their quantitative methods. Same thing for the Reynolds Cup. It's probably the most prestigious of all round-robin mineralogical contests. Yeah? Typically 3 samples are prepared, which are mixtures of pure minerals that represent realistic rock compositions. The rules of the game are very simple. Everyone can participate and all techniques and analysis methods are allowed. The ultimate goal of the contest is to identify and quantify the minerals in the test samples as well as possible. And the winner is declared the laboratory with the lowest cumulative bias, which is being calculated as the weight difference between the reported mineral contents and the actual mineral contents. Also important to note is that participants remain anonymous. Only the top finishers are publicly announced. If we take a little look at the history of the Reynolds Cup, and it's a biannual contest that has been organized since 2002. It was first initiated by Danny Eberl, Jan Schrodon, and Dougal McCarthy, and always under the flag of the Clay Mineral Society. It's been 20 years since the first edition, and the number of participants has actually doubled since then. And typically the laboratories that participate come from academia, public laboratories, but also commercial from all over the world. So we are now through to the 11th edition, which was organized by Q-Mineral, and some acknowledgements are certainly in place. There was some financial support by the Clay Mineral Society, by also the DTTG, and also a big word of thanks to the Royal Belgian Institute for Natural Sciences, where we could sample some of the mineral specimens that were used for the samples in the Reynolds Cup. So if we take a look at the samples that were prepared, so 3 samples were prepared. First of all, there was a shale deposit with 17 phases. And actually, this was a shale deposit that was mimicked to have a little bit of drilling mud in there. So there was a little of barite in there and also a little bit of bentonite. And the challenge here was there was a mixture of dioctahedral clay. So there was dioctahedral mica, there was mixed layer illite smectite, and then there was the sodium smectite, which was then supposed to be the bentonite coming from the drilling mud. And in total, there were approximately 40% of layer silicates in this sample, and there was also some amorphous content, some organic matter. The second sample is a Lacustrine deposit with only 13 phases, more or less the same amount of non-layer silicates and layer silicates. And the challenge is here that there are mainly 3 octahedral clays and also a very high smectite, a relatively high smectite content. In the third sample represents a ball clay deposit. So we naturally have a relatively high layer silicates content with 14 phases. And again, like in the first sample, we have a mixture of dioctahedral clays, dioctahedral mica, illite smectite, mixed layer, and some calcium smectite in this case. And we also had a mixture here of kaolinite and halloysite, which was quite a challenge for this sample. So how did we make the samples? So in the first step, there is evaluation of potential minerals and there is a selection. So we tested approximately 170 potential minerals by X-ray diffraction. So out of that selection, there is a further purification. So either they're pure enough or they need an additional purification with different techniques. Yeah. There is a size reduction, either hand ground or using a centrifugal mill. And after all these preparations, 3 mixtures were prepared of more or less half a kilo each that were weighed out. So each mineral was carefully weighed, so it needs some homogenization. So therefore, overhead tumbling was used 2 times for 12 hours. And in between, the samples were sieved and also homogenized again. After that, they were splitted in 100 equal sample sets, or at least that's always what you hope when you organize this sort of contest. So we did some final testing of the different sample set mixtures with X-ray diffraction and with chemical analysis. So, and that's what you see in this slide. So on the left side, you see for the 3 samples, we took 3 random samples and did X-ray diffraction analysis on them. On the left, you can see that. It's quite homogeneous, but also chemically with ICP, we characterized 3 random samples for the chemical composition. And again, we were quite pleased with the results. So these were safe to send out to all participants. That being said, participants, how many did enter? So we had 93 registrations coming from 29 different countries, as you can see, all over the world. Yeah. Typically, the US and Germany have the most registrations. Finally, we send out 91 sample sets, as 2 labs had withdrawn already by then. And we got back 68 reported results that were being submitted. There were certainly some issues with delivery, so no samples could be delivered to Russia. And there were also some laboratories that indicated there were still some problems with COVID, so they could not access their labs. So this makes that there are not as much submitted results than there were registered. If we took a look at the results, so 68 laboratories reported their results. And typically this you can see on the x-axis here. So these are the different participating labs, and they are being organized in function of their cumulative bias, which is in the y-axis. So the labs on the left have the lowest cumulative bias. The labs on the right have the highest cumulative bias. So typically you can already see there is a very low, by the top finishers, there is a very low total error on the results. If we take a look at the techniques that were being used and the methods, we see that actually all labs have indicated that X-ray diffraction on powders was their primary quantification technique. Yeah. Many labs also used auxiliary techniques, such as oriented slides with X-ray diffraction, chemical methods, electron microscopy or some kind of, thermal methods, infrared, optical microscopy, cation exchange. 3 labs also indicate they use ChemScan, and 2 did also use Raman spectroscopy. So if we take a closer look to the individual samples and the results of those. So in this first sample, it was resembling a shale deposit, and you can see the actual contents here on the left in the table. And on the right, you can see the distribution of the results of the different laboratories. So for instance, for quartz, you can see that the true content was 31.6%. And you can see the histogram of the reported results of the different participants and the distribution being plotted. So what you can see is that actually for the non-layer silicates, we can see that the reported results actually coincide quite well with the actual value. We have a quite broadened distribution, but we can say that most participants do a good job with these non-layer silicates. The same for calcite. Also, there are some outliers. Plagioclase, also the same. It's a little bit of a different story for the amorphous one. as actually more than 20% did not identify the organic matter in this sample. And when it's being detected, the distribution is very skewed and also very wide. So that's a typical feature. If we then look at the clay minerals, you can see here, for instance, for kaolinite, you can see a very broad distribution. Even one could say it's even bimodal. And one of the reasons for that could be that there was not only kaolinite in this sample, but there was also some dicite and necrite. So this could certainly explain this graph, that some participants did not detect the dicite and the necrite, and therefore overestimated the kaolinite, which gave this nice distribution. Then for the dioctahedral mica and illite that were present, is 18%. You see that's a very wide distribution. So, and actually the mode of the distribution does not coincide with the actual content. So same thing for the illite smectite. You see that actually a lot of participants, almost 1 out of 3, does not detect the illite smectite. And you almost get a random distribution when it's being detected. And the same for the mica. It's almost randomly distributed. For the smectite in this sample, it's also the case. 1 out of 3 did not detect the smectite. When it's detected, result is maybe slightly better compared to the other ones, but well, certainly more difficult than the non-layer silicates, that's clear. If we go to sample number 2, we see a very similar picture as with the first sample, mainly normal or almost normal distributions for the non-layer silicates. And you can see here quartz, you can see here calcite, which was the main phase in this sample, plagioclase. We also had potassium feldspar, and it was quite remarkable that actually more than 50% of the participants did not detect the potassium feldspar in this sample. So that's quite remarkable. If we take a look at the clays, this is a quite interesting graph. So here it indicates for the smectite, actually more than half of the participants did not detect any smectite in this sample. So although it's present in more than 20% of the sample, there's certainly a difficulty for detection. And when it's being detected, the results are really random. So there's still some work to do for smectite. For talc, it's certainly better. Talc is being detected by most laboratories, and the distribution in general coincides with the actual content, although you can see distribution is again very, very broad and widened. For the serpentine, we can say it's mostly being underestimated by most labs. Also difficulties for detection for 1 out of 3 labs. And we had a little bit of phlogopite in this sample, which was not always well detected, but when it was detected, it was quite well quantified. Going on to the third sample, which is the ball clay deposit. Again, a very similar result for the non-layer silicates, for the quartz, where the distribution of the reported result coincides with the actual content, but the distribution is quite wide or broadened. Plagioclase is the same. For potassium feldspar, we see the same thing as for sample number 2, which is quite remarkable, that a lot of participants failed to identify this potassium feldspar. So, interesting result over here. And we also had a little bit of amorphous, but it's really low, so it's normal that it's not being detected well. But if it's detected, and that seems to be very universal for amorphous phases, also from previous contests, is that you get a very broad distribution of reported results that are almost random. And in this case, it maybe could be that a lot of the clays are being misidentified for amorphous phase, actually. If we then take a look at the clay minerals for this sample, You see that kaolinite for the mode of the distribution of reported results coincides quite well, but we get a very broad result again for the kaolinite. The halloysite, which was in there, yeah, the results are quite poor, as you can see. So actually, almost 2 out of 3 participants fails to identify this 10% of halloysite in the sample. And when it's being detected, yeah, the results are random. So halloysite, difficult one to quantify and identify. Same story almost for the illite smectite here. 1 out of 3 did not identify it. And we have some smectite here, some calcium smectite is also better detected, but quantification remains quite hard. So let us progress to the details of the top finishers. And as you can see here in the table, this is actually the sum of the cumulative bias. And you can see that the average bias is 159 over the 3 samples. And the top 10 is all within 100, which is quite a good result. But look at these two guys, 46 and 35.2 for the top, the first place is actually, if I'm correct, is the best achieved bias throughout the last editions of the Reynolds Cup. So very impressive results here. So let's go to the announcement of the top finishers. So in 4th place is the team from BGR, and Christian, Stefan and Rainer are one of the usual suspects that you expect among these top finishers. And they're very consistent in their results. So I think in almost all Reynolds Cup editions, they end up in the top 10 or even in the top 5. So a very strong team over here with a bias of 77.2. And then in 3rd place, we have 3 teams that have joined, so because they have a bias which is very close together. So the first is the team of Bruno Lançon, Stanislav Jelavic and Nathaniel Feindling of ISTER in France with a bias of 73.4. So this team also performed very well in the last Reynolds Cup edition. So they confirm their quality in quantification and mineral characterization. We have the team of the Polish Academy of Science. Most of you will recognize Arik Derkowski or Mike Scherba and their team. They had a bias of 71.9. And also they are one of the usual suspects, they are very consistent in their mineral quantification results, being among the top finishers in a lot of the previous Reynolds Cup editions as well. So well done, guys. Also 3rd place joined is the team of Peter Ulek of the Comenius University in Bratislava in Slovakia. They did very well. As I'm correct, they were not amongst the top finishers in previous Reynolds Cup editions, so they have really done a very great job in this edition. So congratulations, guys. In 2nd place, with an incredible bias of 46.0, is the team of Mark Raven and Peter Self and their co-workers of CSRO Australia. And actually this team is also, it's not even one of the usual suspects, it is a consistent top finisher. Out of the 4 last Reynolds Cup editions, Mark has ended up 3 times in 2nd place. So he's used to be a runner-up, but this time I know he's a little bit disappointed, and I can understand it, because with a bias of 46, you would expect to win it at any time, and it also would have been well-deserved. So congratulations. But there's one team that even got a lower bias of 35.2. And here you can see the results of that team. On the left, you see the results of the non-layer silicates, so the non-clays. And in green is the bias of each phase. And you can see that for the non-clays, it's systematically below 1%. So very impressive work. On the right, there is the clay phases, which are also typically the bias is a little bit higher there, but still look at the second sample. Overall, a very impressive result, which got them to a bias of 35.2, which is the lowest achieved bias in all Reynolds Cup editions, if I'm correct. So nice job. And the winners, here are the new champions. Yeah, no surprises there. Steve Hillier and Helen Pendlowski from the James Hutton Institute in Scotland. Yeah, as most of you know, Steve is Mr. Reynolds Cup. Yeah. He has ended up in the top 3 in every Reynolds Cup edition he has entered. So really great stuff from Steve there. Being consistent among the top 3 is really impressive stuff. So big congratulations to Steve, and also to the other participants, of course. I hope you have learned a lot. Coming to the end of my presentation here. Thank you for participating. It was also an honor for me to organize this Reynolds Cup edition again, but I like it more to be on the other side and participate again in 2024. So see you all then.